Hello, all of you. Welcome to the second week of lectures in the course on analysis and modeling in chemical engineering. In the last week, I have given you some overview of what is chemical engineering, what is modeling and analysis, and we have taken some, I would say, a daily life kind of examples of the time to travel, and I also taken the example of a spring dashpot problem just to demonstrate what exactly modeling entails, what is the meaning of assumptions, what are the steps of modeling, and then I finally came up with the idea of the recipe of doing the modeling. We discussed three kinds of models: the fundamental model, empirical model, and modeling by analogy, which we demonstrated for the spring dashpot problem. And then for the time to travel for problem, we discussed the hierarchical kind of an approach where we begin from a very simplistic model, assuming like there is no traffic and the car is going at a constant speed, to a more detailed complex model with fewer assumptions that considers the effect of traffic and heterogeneity in the traffic and things like that, right? So in this week, the agenda is to recap some of the concepts that you have learned in chemical engineering, which we require in the coming up weeks as well. And the other idea is to kind of tell you how exactly all these concepts are kind of intertwined. When we learn in UG curriculum, chemical engineering UG curriculum, these different concepts are taught in a certain fashion, but then there is not much emphasis typically, or the time is not there to basically see what is the relation between the different concepts and principles. And as much as possible, I will try to also tell you about certain misconception or myths that are prevalent in the field, just to make you clear about some of the concepts in there, right? By no means in the 5 lectures we can replace what is typically taught in the subjects in the undergrad, but it is more to like give you an overview and try to see the correlation between the different things and things like that. And of course, wherever you find a problem in a certain concept, the first point is to go back and read that subject or look at the videos for that subject and things like that. Okay. So basically these are, if I have to say, the fundamental principles in chemical engineering. These are basically the fundamental principles. They may come by different subject names, but these are the fundamental principles that you typically learn in chemical engineering. You begin with the equations of motion, that is typically coming in the courses on fluid mechanics. Then you have transport equation, the momentum transport, thermal transport or heat transport, and then mass transport, that is typically taught in transport phenomena course, or also as part of fluid mechanics heat transfer and mass transfer courses. Then one thing that is typically common in almost all the courses that you have taken in undergrad chemical engineering is the idea of material balance and energy balance. Thermodynamics, there are dedicated courses, but what I want to emphasize here and try to convince you is thermodynamics is kind of everywhere. So we'll see how thermodynamics is related to the idea of transport and other things like kinetics and things like that. And finally, particularly in the courses on material balance or chemical reaction engineering, you must have learned the laws of chemical kinetics, chemical equilibrium, and particularly for mass transfer courses or courses on separations, you must have learned the idea of phase equilibrium, which I again will try to connect these ideas with thermodynamics and other things in this particular course. So I will begin with these concepts one by one and try to give you sort of an overview and try to probably clear certain misconceptions that you may probably have. But again, I emphasize this is by no means a replacement of the full course on any of this. So we begin with the equation of motion, and if we have to think about it, this is pretty much not a thing in chemical engineering. This is something that comes from like classical physics, the Newton's laws of motion. The force acting on an object is simply the mass times acceleration, and this we already have used in the example on spring and dashpot. We can define the velocity as the derivative of the position, acceleration as the second derivative, again with respect to time. But then when we look at the problems in chemical engineering, then the same equation of motion manifest in different ways. The reason being that the forces that are acting on an object, these forces are very different in nature depending on the system that we are looking at. So, I am showing you here 3 examples. These are pretty much the problems that we encountered in chemical engineering, but in the 3 examples, the way the equation of motion is employed or the nature of the forces are very different, right. So, the very first example is example of a ball that is dropped in a viscous liquid, and you may have done an experiment in the fluid mechanics lab where you probably are interested in finding the terminal velocity of the ball, the velocity once it hits the bottom and things like that. So, if you look at this problem, then you have a ball and then you have a viscous liquid which may have a certain viscosity, and clearly the ball has to be heavier than the fluid. So, probably the ball has certain density, let me call it rho p, and the density of the fluid can be, let us say, rho. Then in this particular case, if I assume that the ball also has a volume v, then there is a gravitational force acting on the ball that is given as something like rho p v, that becomes the mass multiplied with the gravity. This is my gravitational force acting in the downward direction, and this is being opposed by 2 forces. One is the buoyancy of the fluid, that is given as the volume of the fluid that is displaced multiplied by its density. That means that effectively the mass of the fluid that is being displaced, that gives the buoyant force. So, that is going to be something like minus rho v and g, that acts in the opposite direction. So, buoyancy acts in this direction, the gravity acts in this direction, right. And then finally, there are viscous forces that resist the motion, right, and that is typically proportional to the velocity of the fluid, and that is also in the opposite direction. So, you have something like, let me tell you, some constant k multiplied by the velocity, where k is, there are empirical relations for that, but one of the relations is something like this: k is 6 pi eta r, where eta is the viscosity. Eta in principle may depend on the shear rate, but if it is Newtonian, then eta is constant, and eta is equal to a constant value mu for the Newtonian liquid. Of course, this is an empirical relation, so there are limits to applicability of this particular relation, right. But other than that, the fact that the viscous force that resists the motion is proportional to the velocity is somewhat general. So, we can take it that way. So, this is the force balance on this object, and this net force acting on the object will naturally give rise to the acceleration of the object in the downward direction, and that is equal to again the mass of the object, which is rho p v, the mass of the ball, the object here, rho p v, this is the mass multiplied by the acceleration. Acceleration is, as I said, first derivative of the velocity or second derivative of the position, right. So, this is how the equation motion is applying for this problem. Now, let us take another problem where I am looking at particles, and I am talking about particles that are fairly small. They are like colloidal particles, right. If you think about, let us say, milk, then milk is kind of a colloid. There are particles in the milk that basically give it the thickening effect that you see there, and these colloidal particles are typically fairly small compared to the ball that is falling under gravity in the experiment I was telling you. So, again it has a mass, again these particles have a mass, but this mass or the corresponding volume is fairly small, maybe in the range of the diameter of the particles may be in the range of a microns, right. And again it is suspended in a liquid. So, liquid naturally has a certain viscosity, and of course, the liquid has a density rho, and the particle itself may have again some density rho p, right. Now, if I look at this particular suspension, and if it were like the example of the ball dropped in a viscous liquid, what is going to happen in this case is all these particles will eventually sediment and settle at the bottom, right. So, over time you will see that all the particles, whatever is there, they will come to the bottom and there is nothing left on the top if the gravity is the dominant force, right. But in a suspension that does not happen, right. So, of course, there are viscous forces, there is a gravity, there are buoyant forces, right, but these are no longer dominant in the system. What I mean to say is that if it is forming a suspension, then these forces must be negligible or small, and some other forces must be coming into existence, because if these forces were dominant, then all the particles can sediment and go to the bottom. That indeed happens if particles were big enough or particles are heavier enough. Let us say if you have steel particles, right, even if it is 1 micron, it is going to settle down. But if it is like a polymeric particle that is of the order of micron, they may, and I will take some examples later, they may remain suspended in the liquid, right. So, what additional forces do arise in this system, right? Couple of forces. One is that there is going to be a certain interaction between different particles. So, you have many particles, and there are interparticle forces exerting between these particles. What are these interparticle forces? If, for example, the particles, the colloids possess a charge, then there can be electrostatic repulsion or attraction between the particles. If all the particles are identical, then there is going to be a repulsion between the particles. And I will take an example later how this repulsion basically stabilizes the suspension. That is the reason why the particles remain in there, right. But other than this electrostatic force, there may be, like, for example, some short range forces, what is called the van der Waals force between the particles, that may also exist. And now, if you think about it, we have something like this. So, the force that is acting on a particle, let me call that particle I, that is because of all the other particles in the system, right. So, let us say, for example, I number this particle as 1, then there is a force acting on I because of this particle 1. Let me call that force something like force acting on I because of 1. Similarly, there is a force acting on I because of particle number 2, and similarly for particle number 3, 4, and so on. And the force that is therefore acting on the particle I is now the sum over the interparticle forces for all the values of, let us say, j from 1 to n, if there are n particles in the system, and clearly the particle does not exert force on itself. So, we exclude the case when j is not equal to, we exclude the case when j is equal to I, and we will have these forces F I because of j, right. So, in addition to the gravity force, buoyancy force, and the viscous force, now there is this new force that is coming from this interparticle interactions. They are also present when it would have been a bigger particle, but then the magnitude of that is going to be very small. For example, I am standing here, another guy comes here, we may have an interparticle force between us, but that force is going to be negligible in comparison to our gravity force and buoyancy force and things like that, right. So, these interparticle forces become very important once we are looking at smaller particles and also at probably smaller distances. These forces are much larger at very small distance, and as the distance increases, these forces decay very fast. So, this force is typically expressed in terms of what is known as the interaction energy between the particles, and in fact, it is something like the derivative of the interaction energy, this u between the particles, and the interaction energy does actually decreases as the distance increases between particles, right. So, for example, if you have a Coulombic force, it is kind of proportional to 1 over r, right. The full expression is something like 1 by 4 pi epsilon naught epsilon and on top we have Qi, Qj. So, you have charges on the particles I and j, and then there is a dielectric constant that is given by epsilon naught epsilon, and then finally there is a r, that is distance between the particles, right. So, if I plot this Coulombic interaction versus r, it is going to decay something like this. On the other hand, if you have a short range force, let us say a van der Waals force, the van der Waals force goes something like 1 over r to the power 6th. So, that is going to decay much faster with respect to r. So, the point being that whatever is the force that is acting between these particles, their range is fairly small. So, only when we look at smaller particles at small distances, then only these forces come into play, and therefore, they are not considered when there was a ball falling under gravity in the example there. There may have been other balls there, but the interparticle interaction between them is not important in that problem, because the balls are big enough and the distances are fairly large, right. So, this is the second problem, where the gravity, the buoyancy and the viscous forces, they are still there, but not driving the behavior. But now I take a third example that may look something similar to the second example, but it is a fairly different example, where we have something like what you see in a flour mill. So, you have flour that is being crushed, and on top of that you pretty much load the particles there that get crushed and forms the flour. So, this is what is known as a granular system. The particles are much larger to begin with compared to the previous example, but maybe much smaller than the earlier examples. It is in between these two extremes, right. And now the ball is no longer, the particles are no longer in the viscous liquid, it is present in air, and air, as you know, is not having such a high viscosity. Of course, air may present a drag force, but the viscosity is fairly low. So, now here again we can write an equation of motion, and what is more important here, which was probably not that important in the other two cases, is how often these particles collide with the other particles. Because you may imagine that you have kind of a flour mill and the particles are eventually getting crushed, but before that you have a high density of particles, a large number of particles in a small volume, and there are going to be many frequent collisions between these particles. So, we will again solve the equation of motions, but now we need to look at how many collision events are happening in this system, at what frequency and things like that. So, when we solve the equation of motion of this system, now we have to account for the collision more efficiently, right. So, you can see there are three different problems. In all these problems, we are applying the equation of motion F equal to ma, or maybe a momentum balance, whatever you think is appropriate, but the type of the forces are different, the physics is different, and therefore, the final solution, whatever we get by modeling this, is going to be very different. But the fundamental idea is, again, all of them are driven by the equations of motion. So, this is I would say three common examples. There are others, and I will come to some in the future. So, now when we talk about this motion, when we use this equation of motion in, let us say, fluid mechanics, we take many a times a very different idea altogether. Let us say, when I am saying that a fluid is moving through a pipe. So, of course, the fluid, let us say water, is composed of molecules, right. So, water is having an oxygen and two hydrogens. So, you may imagine that there are these molecules which are moving in the pipe, but when we write, let us say, equations to find the pressure drop in a pipe, we do not really worry about the chemical structure of water. We treat water as something known as a continuum. What do we mean by this continuum? What we mean here is that, let us say, a fluid is flowing in a pipe. What I assume is, let us say, I am interested in finding the velocity here, the velocity in this particular volume. Then, of course, this velocity in this volume, whatever I have drawn, is going to be a measure of what is the velocity of the molecules in that volume, but not quite. It is some kind of a measure of the average velocity of all the molecules within a particular volume. And that volume is typically referred in literature as the control volume, right? And the way it is typically used is like the following. So, we no longer say that we have a volume necessarily, of course, it is used in derivation. What we say, at any point in the fluid, I can define a velocity, and this velocity is not of a fluid molecule, but it is the velocity of all the molecules in a control volume I can draw around this particular point, and some kind of an average of that, right. So, a very small control volume, if I have to put a number, let us say I draw a control volume of, let us say, 1 micron around a particular point. Then in that 1 micron cubed volume, you will have a very large number of molecules. So, the velocity at a point that we define in fluid mechanics is the average velocity of such a large number of molecules in that 1 micron cube volume, if I might, in that control volume around the particle. The same is true when we go to heat transfer and we talk about temperature, right. As I will discuss later, and you may have learnt earlier, that temperature is a measure of the kinetic energy of molecules, right, average kinetic energy of molecules. But we do not take that picture when we do a typical heat transfer. What we say is again like velocity. If I have, let us say, some equipment, I define a temperature at a particular point, and that temperature again is some kind of a measure of the average kinetic energy in a control volume, which I can draw around this particular point, right. And the same is true for concentration, right. Concentration is the number of moles per unit volume. Moles is Avogadro number multiplied by the number of molecules, right. So, concentration basically should tell us how many molecules we have in a certain volume, but then we do not define it that way. We say that, let us say, I have a vessel, I have a point, and I define a concentration at that particular point, right. And now I am saying that the concentration may change with position, right. So, in that case again, what I am telling essentially is, if I draw a small control volume around this point, what is the number of molecules per unit volume, maybe on an average level, around this particular point. How can we do that? In all these cases, I am completely disregarding the fact that the molecules have certain velocity, or the kinetic energy may vary, or the number of molecules per unit volume can vary, and things like that. Of course, that is true. So, this approximation is only true if the characteristic length of my system, let us say the pipe diameter or the vessel diameter, whatever we have there, is much larger than a typical control volume I can draw. Let us say, for example, if this was 1 meter. So, even if I take this control volume to be like something like 1 micron in size, I have a very large number of molecules in 1 micron cubed volume, right. So, therefore, I can take an average and define the velocity at a particular point, or the average kinetic energy or temperature at a particular point, or the concentration at a particular time, right. So, this idea of a continuum applies when we have the characteristic length of the system much bigger than a small length scale, which can make up my control volume, and that length scale should have a fairly large number of molecules, right. So, approximation will work only when the characteristic length is much bigger than, let us say, the molecular length scale, right. So, for example, if I now take that my pipe is, let us say, 1 micron in diameter, now I can no longer do that, because now if I look at a point, I cannot draw such a big control volume around that point, and even if I do, there are going to be very large variations, or the number of molecules will not be sufficient to compute the average, right. So, the whole notion of continuum approximation will break down as soon as we start going to micron level length scales, right. That is the reason why microfluidic systems or nano systems behave very differently than compared to the bigger size systems that we are typically known as, right. So, now what we can then define is for a particular point in my system, let us say the point is having a position at that particular point, I can define the velocity, which is now a function of, let us say I look at some other point here r prime, then the velocity will be velocity of r prime at that point. And I can also define the temperature and the concentration. That is how we typically define the velocity, temperature and concentration, which are position dependent. And then I can also define the flux from this control volume, the net flux from this control volume, or in the language we typically say the net flux at this particular point, right. So, whenever I am referring to a point, keep in mind that it is not exactly a point, it is a small volume that I am looking at, very, very small volume compared to the bigger volume of the system, over which I am doing an averaging of the number of molecules and finding the property. And this approximation is good when we have like fairly large characteristic length compared to the molecular length scale. So, I can define momentum flux, that defines how the momentum is changing or the velocity is changing in the system. A thermal flux or a heat flux that determines how the temperature is changing in the system. And then finally, a mass flux that tells me how the concentration is changing in this particular system. So, with that, then we go ahead and derive what is known as the transport equations for the system. And the transport equation are the fairly common equation that we use, that is using the idea that the flux is assumed to be proportional to the driving force, and the proportionality constant is some constant for the system. It is again just like Hooke's law we have looked at in the spring dashpot problem, is not always true, but many a times valid or more commonly valid. But there is of course limits of applicability of this law. So, let us say for momentum flux, we typically say it is the viscosity mu times the velocity gradient, which is true for a Newtonian liquid. For a heat flux, we say it is thermal conductivity times the temperature gradient, all with a negative sign, keep in mind the negative sign here, and that is true for conduction problems, and it is called Fourier's law. Again, it is limited to a particular limit that we can discuss, but it is not always true. There are of course limits of validity on all of these models. And finally, for the mass flux, we have the constant as the diffusivity, and the driving force is the concentration gradient, right. So, the gradient of velocity, the gradient of temperature, the gradient of concentration, they become the driving forces. The viscosity, thermal conductivity, diffusivity becomes the constants, and essentially if you look at it, these three definitions are for three different contexts. For fluid mechanics, we have the first one. For heat transfer, we have the second one, and for mass transfer, we have the third one. But the basic form of all these fluxes is pretty much same, right. So, I hope I have been able to convince you the commonalities between at least the fluid mechanics, heat transfer and mass transfer, and I will tell you more about these kind of commonality later also in this particular course, right. So, with that, I want to conclude here, and to summarize, what I want to say is we have discussed this fundamental laws. Now, we have started from the equation of motion, and we also discussed the idea of continuum, transport equations, and what we are trying to look at is how the different concepts that you learn in chemical engineering are intertwined with each other. So, in the next class, we will take up more examples on these and tell you about more fundamental laws in chemical engineering. So, with that, I want to stop here. Thank you.